Welcome all of you to the course on Renewable Energy Sources, Fundamentals and Technologies. Since it's the first lecture, let me introduce myself. My name is Professor Sonal K. Thengne. I am Associate Professor in the Department of Hydro and Renewable Energy, IIT Roorkee. I joined here in 2020, and since then I have been teaching this course on renewable energy sources in my department. So, considering it as a first lecture, I think let's first go through the syllabus and then the content for the today's lecture. So, this course syllabus, as the name indicates, renewable energy sources, fundamentals and technologies. So, there are different types of renewable energy sources like solar, wind, biomass, hydro, geothermal. So, we will be studying about the fundamentals about all these technologies first, and then see what are the advancements so far as technologies are concerned in these renewable sources. So, we'll start with the introduction where we'll look at the global energy scenario, the Indian energy scenario, some basic definitions related to energy, work, power or electricity, and what is the need for renewable energy and what's the driving force behind, like as we see, like the entire world is moving towards renewable energy to address the issues of climate change and global warming. So, we'll see like what are the other factors which pushes the world or the global energy transition towards renewable energy. And since directly or indirectly all the energies come from sun, the first and the technology that we will be talking about is solar energy. This unit will cover some basics about solar geometry, the different types of radiations from solar energy, solar PV technologies and solar thermal technologies, because these are the two major routes by which we can utilize solar energy. The second would be biomass. So, there are different sources of biomass coming from plants, animals, municipal sources, industrial sources, forestry, agriculture. Okay, so we'll look at those sources, some properties, characterization, and in conversion we will look at primarily thermochemical conversion processes of biomass, followed by biochemical conversion processes for biomass. Next in line would be hydropower and wind power. I am showing them together because some of the aspects related to like types of turbines and plant components would be quite similar in both the technologies, but yes, we will be studying them separately with respect to their plant components, turbines, efficiency. And in wind power, we'll look at the derivation for power equation, Betz limit, and again the different types of windmills or turbines, along with generators that are used in the wind power plant. Last, we'll also look at some brief overview and technologies related to geothermal, ocean and hydrogen, because hydrogen is also considered as a like energy carrier and can be a game changer so far as energy storage is concerned and transportation sector is concerned. So, we'll have like maybe couple of lectures on hydrogen also. Towards the end, we will discuss India's renewable energy roadmap on the basis of its policies, market and challenges. And when I say case studies, it is actually connected to each of these renewable sources. So, whenever we study about solar or biomass, we will be going through some real world case studies, particularly in India, focusing on those technologies. So, that sort of covers the entire syllabus for this 20 hours or like say 8 weeks of course on renewable energy sources, fundamentals and technologies. Coming to the lecture content today. So, today we will start with some basic definitions and then move towards energy sources and classification of those energy sources, finally ending with the need or the importance of renewable energy. So, the first concept, energy. What is energy? We all have studied in the school books that it's a capacity or ability to do work. Yeah, it's the same definition, capacity or ability to do work or cause a change in matter. And this energy has different units depending on which sector we are using the term energy. Like if it is related to heat, we would be using the unit of joule. If it is related to electricity, we would be using kilowatt hour. And if it is energy related to say food, we talk in terms of calorie, where 1 calorie is 4.184 joule. And since energy is a property which depends only on the magnitude and not on the direction, it is a scalar quantity. There are two major forms of energies depending on whether the body is in like having a stored energy or whether it's in motion. So first one is potential energy, which we define as mgh, where m is the mass, g is the acceleration due to gravity, whose value is around 9.8 meter per second square, because we are talking with reference to earth, and h is the height of the object from the surface of the earth. And second is kinetic energy, which depends on the mass and velocity of the body. So there are different types of potential energy and different types of kinetic energy, as you can see in this picture. Most common type of potential energy is chemical energy, which we obtain from like maybe fossil fuels like coal, oil, gas. They all have a lot of chemical energy stored in their hydrocarbon bonds, right? And when we combust them or burn them, the energy is released as exothermic reaction. Then we have mechanical stored energy, something like pulling a trigger or pulling the bow arrow and holding that. So that's a stored mechanical energy, and the moment we leave that arrow, it converts to kinetic energy. Then gravitational potential energy and nuclear energy. In kinetic energy, it's about the energy which is in motion. So it's mainly electrical energy, where the energy is carried by the flow of electrons, ions, or holes if it's a semiconductor. Then radiant energy, it's carried by light. Thermal energy carried by heat. Then motion energy and sound energy. Sound energy is also like because of vibrations, and there are crests and troughs because of the movement of the particles in the medium, and sound waves travel through that. So that was all about energy. The second is work. So work is related to energy because it happens only when there is a transfer of energy. So when an object is displaced by an external force in the direction of that particular force, then we call that there has been an energy transfer that has occurred, which is actually called as defined as work. For example, here you can see the person pulling a box with the force F, and this box is getting displaced by distance d. And since force and displacement both are like say vector quantities, so work is actually defined as the dot product of two vectors, f and f dot d, and dot product of two vectors is a scalar. So that's why work is also a scalar quantity which won't depend on the direction but only on the magnitude of the quantity. And the unit of work is similar to energy, it is joule, and it can be also related in the form of Newton meter or kg meter per second square meter, because the force has a unit Newton. So that's the work for which we need energy. And the third concept, which talks about the rate of energy transfer or the rate of work done, is called as power. So power is nothing but rate of energy transfer or the rate at which work is done. So we have work divided by time, that gives you power. And work we have seen like force into displacement, and time is there. Distance by time is nothing but velocity. If you remember the unit of velocity, it's displacement by time or distance upon time. So these are different formulas that can be used for calculating power. It is also a scalar quantity, because since work is a scalar quantity, time is scalar. It doesn't depend on direction, it depends only on magnitude. So the division of these two quantities, it's going to be a scalar, and the units of power is going to be joule per second, which is also called as watt, or sometimes in commercial world we use the units of horsepower. And there are two types of horsepower basically. It depends on the connection between the power employed by a horse or a pony, and in different parts of the world we use different. There are two major definitions of horsepower. One is imperial and one is metric. So as you can see in this picture, the imperial horsepower, it is based on 550 pounds of mass lifted by 1 feet in 1 second, which comes out to be 746 watts. And in metric horsepower, which is most commonly used in Europe and Asia. Unlike the imperial horsepower which is used in US and UK, the distance is measured in metrics, like 75 kg lifted by 1 meter in 1 second gives you 736 watts. So there is a difference of only 10 watt in both the definitions, but it depends on, like in India, like if you go through different machineries, mainly the pumps or the cars or the motors, depending on where they are imported from, whether if they are imported from US and UK, they will have the units in terms of imperial horsepower, but if they are made in Europe and Asia, they will have the units of metric horsepower. But the way it is calculated, by multiplying mass by like delta H and divide by T. One simple, like I can do for metric, so it is like 75. This is the mass, and the weight or the work done for lifting this mass would be 75 into 9.8, which is acceleration due to gravity, divided by 1. So this comes out to be 736 watt approximately. That's why metric horsepower unit is 736 watt. So now with those basic definitions of energy, work and power, let's move towards the type of energy and power which we are more interested in this course, which is electrical energy and electrical power. Their definition is also going to be similar based on energy and power, but with respect to the electrons or the electricity. So electrical energy is the total work done by electric charge moving through a potential difference or voltage V, representing the capacity to do work. So if we have, like say the equipment has power P rating and it is used for time T, the energy transferred or the work done would be power into time, and power is voltage into current, that is VIT. And by Ohm's law, if you remember, voltage is directly proportional to the current, and the constant of proportionality is called the resistance. So V equal to IR. If you substitute that, we can get energy in terms of I square RT, where unit is joule or kilowatt hour. The electricity bills that we get in our houses, if you go through it, you will see this number written there, units. At some states there will be like free 100 units, and then after that you may get charged. So that unit, 1 unit is nothing but 1 kilowatt hour. It represents the electrical energy in the unit of kilowatt hour. It means the 1 kilowatt power rating equipment is used for 1 hour. That's the equivalent 1 kilowatt hour. So electrical power, it is again the rate of work done, the rate of electrical work done, the rate at which work, basically the movement of charges, is done in an electrical circuit, or the rate of consumption of electrical energy by a device. That is called as electrical power. It's defined as potential difference or voltage into current, and unit will be joule per second or watt or kilowatt. It can go all the way to megawatt or gigawatt. Those are just the higher multiples of the basic unit, which is watt. So now we have seen the definition on the difference between electrical energy and electrical power. And now if I ask you a question like, what do you mean by electricity? Because in real world, we keep on using this term interchangeably. If there is a power cut or a electricity cut, sometimes we say power has gone, sometimes we say energy has gone, sometimes we say there is no electricity. Okay, so because of the common interchangeable use of these terms in daily life, it becomes confusing sometimes, like which term is actually correct. So let's look at what exactly is electricity. Electricity is not a measurement, it's not a property, it is the physical phenomena itself. If you have to define it, you can define it as the presence and flow of electric charge. Okay, it's a flow, presence and flow of electric charge, or it can be called as a medium through which electrical energy can be transferred. So that's the definition or the difference between electricity, electrical energy and electrical power. Let me try to explain it with the example of this water hose system. Also before that, electricity, it can be of 2 types. You see the static electricity. If you rub a balloon or if you rub a pen through here and try to lift up the pieces of paper, which we used to play a lot in our school days. So that electricity, which is because of the friction and charge, it's called static electricity. And current electricity is what we get flowing through our electrical lines and cables to electric devices. It will be mainly through the flow of electrons or electrons and holes. In some cases, it can be through the flow of ions also. So, if we have a hose, like if we have a tap, the hose, there is a water flow, and then we use the water. So, this entire system can be called as electricity. It's not a quantity, okay? It's just a general physical phenomena which has the concept of water flow and the pressure, that can be called as electricity. Now, if you look at the total volume or the total work done or the energy stored as water in the form of in this bucket, or how much water is actually used, that total volume is nothing but electrical energy. So, it is a measurable quantity, and electrical power is the rate at which this water is being filled or water is being used. So, if we have high power, it means large flow rate. If we have small flow rate, if we have low power. So, that power is voltage into current, that shows you the flow rate. So, the system is electricity, the total volume of that system is electrical energy, and the flow rate of that volume can be called as electrical power. So, hope that distinguishes the three concepts of electrical power, electrical energy and electricity for you. Let us do one simple numerical to see like what's the energy and like what's the difference in energy and power, or how we can calculate the same number in different units. So, if we have a 220 volt 1 ampere electric lamp to provide light for 30 minutes, can you find energy in kilojoules and kilowatt hour? And assuming that if we use it for 1 month, that is the month of June, which has like say 30 days non-stop. So, it means 30 days into 24 hours it is used non-stop. How much will it add to the electricity bill? You can assume 6 rupees per unit. So, what do we need to find? Energy. Okay. So, what is electrical energy? It's power into time. Power is voltage into current into time. Voltage is given to you 220, current is given 1 ampere, and time is also given, that is 30 minutes. If I convert it into seconds, you can multiply it by 60. So, 220 into 1800, it will come out to be 39600 something. So, that is watt per second. If I convert it to kilojoule, we can just divide it by 1000. So, we get kilo. Watt second is joule. So, kilowatt second is kilojoule. So, that is the first part of the answer. We got electrical energy in kilojoule. Now, if you want to convert it into kilowatt hour, there are direct correlations like 1 kilowatt equals 3600 joule. But if you do not know those correlations, we can still follow the same approach and try to find. Electric energy is 0.22 kilowatt, because it is like 220 watt, 220 into 1. So, it is in watt. So, if I convert it to kilowatt, it is 0.22. 30 minutes, if I convert it into hour, how much will it be? 0.5 hours. So, 0.5 into 0.22, it is 0.11 kilowatt hour. If you multiply this number by 3600, you will get this number 396. So, that is why we calculated electric energy in both kilojoule and kilowatt hour. Now, the second part of the question is, if we use it for 1 month non-stop, so units consumed for month of June would be 30 into 24 hours into the rating, that is 0.22 kilowatt. So, it comes out to be 158. Now, this is the total number of units. Per unit price is 6 rupees. So, what will be the additional cost to the electricity bill? It will be 6 into 158, it comes out to be 950 rupees. So, this is a simple numerical to help you understand how we can use the power and energy interchangeably and calculate energy in different units, and how it is affecting the monthly bill also if we know the electricity tariff, that is the price per unit. This slide shows the common appliances that we use in our houses, and you can see the rating or the electric energy consumed in each of those equipment. It goes on increasing as we move from lights and TVs and CFL fan or refrigerator to all the way to geysers, air conditioner, geyser and washing machines. So what can you see here? Like when there is just direct conversion of electricity and usage of electricity in the form of here like light or small motors, the consumption is less. But when we try to use electricity for large power requirement, like for say heating, it will have the highest energy demand. For motors, it will have like medium energy demand, and for electronics and lighting, it is low. Washing machines and dryers, they have the combination of both the heating demand as well as the motor requirement, and those motors spinning with all those clothes and water inside the washer, it consumes a lot of power. Similarly in geyser, like we heat water at a very fast rate, so a lot of work has to be done in a short time, so there the power requirement is very high. So that's why you can see the varying power requirements in different types of equipment that are being used at home. So the idea behind showing this was like everyone knows what are the appliances at their homes, and if these are the approximate ratings, and if you know the monthly consumption or the monthly usage of these products, you can just do some simple numerical calculation and calculate the number of units consumed and cross check with your electricity bill whether it's coming plus minus 10-20% what the bill says or not. The main source of energy, obviously it's the sun, because directly or indirectly all the energy in this world is coming from sun. There are few exceptions, like which physicists also called as stellar sources, which can be for nuclear and some aspects of geothermal, but majorly whatever energy we see here around us comes from sun. And the source of energy for sun is the process or the reaction called as nuclear fusion. What happens in this reaction? Because of very high temperatures and pressures inside the sun's core, which is in like say millions and billion, so million degrees Celsius or billion bar, such high pressure and temperature, the hydrogen atoms which are there inside the sun, they fall apart and their nuclei, they fuse together. So like 4 nuclei of hydrogen atoms, they fuse together to form one helium atom. But what happens during this reaction, the mass of that one helium atom is not equal to the mass of these 4 hydrogen nuclei. It is always less than the mass of that hydrogen nuclei. So that difference in mass is emitted in the form of energy or heat and light which we get from sun, and that process is called as nuclear fusion. So sun's high pressure and hot temperature, they cause hydrogen atoms to come apart and their nuclei to fuse to form a helium atom, and the mass of that helium atom is always less than the mass of the 4 nuclei that were combined or fused to form them, and that difference in mass is released as energy, which is called as nuclear fusion. So this energy, when it reaches the surface of earth, it goes to the plants, it can be obtained in the form of fossil fuels million years later. It can be responsible for renewables like solar, wind, hydro, and all these energies then ultimately is used by human beings or animals or biodiversity for different purposes. Can be for electricity, can be for transportation, can be for consumption, but all these energies, as you can see, in the form of light or heat, it comes directly from the sun. So when that main source of energy is sun, we'll study about it in more detail when we talk about solar energy. But now, since all the energy sources come directly or indirectly from the sun, let's see how we can classify them. So the basic way to classify energy sources, whether it's renewable, non-renewable, it doesn't matter. We can call it as primary and secondary. Depending on the one which are either found or stored in nature, it can be directly, some of them can be directly used. So those are the primary energy sources. For example, fossil fuels, coal, oil, gas, even biomass, hydro and nuclear, they are found in nature and they can be directly used or they can be processed and later used again. So those are the primary sources. Secondary, these are mostly the industrial utilities and energy sources which are produced from the primary sources like steam, electricity, heat and chemicals, and then we use these secondary sources for satisfying our requirement. So that's the difference between primary and secondary. The second way we can classify the energy sources is renewable and non-renewable. Renewable, as the name suggests, they keep on getting renewed in nature. They are not exhaustible, continuously produced in nature, like solar, biomass, geo, wind, tidal, hydro, all these things. Non-renewable, they are accumulated in nature for a long time and cannot be replaced timely if exhausted, because it took millions of years to form this coal, oil and gas, and if we consume coal today, the same amount of coal, it will take much long time to get it formed. So the timely replacement, if we take a reference of one human life generation, like say 100 years or 200 years, it cannot be replaced, and that's why those are called non-renewable energy sources. So these were the classification that on the two bases: primary, secondary, renewable, non-renewable. Next, now since we have seen different sources, ultimately the sun is the source, we have seen different types of energy. The question is the world running out of energy? No, the world is definitely not running out of energy. As long as sun is there, energy is going to be there. So what are we running out of? Can the world run out of fossil fuels? Yeah, that's a possibility. That's a possibility, and that's why there is a need to find alternatives to fossil fuels like renewables. So coming to the last point of the today's lecture, why renewable energy? The one thing is, obviously, if a day comes when we run out of fossil fuel, we need to have renewables. But there are other reasons also. It's a solution to issues of climate change, emissions and energy security. They are clean and eco-friendly with long-term certainty, because sun, wind, hydro, they are going to be there. Oceans, water, they are going to be there. So if we develop technologies that can generate energy from these renewable sources, they have a long-term certainty, definitely, than the fossil fuels. Other reason why it is important, the investment in this sector, whether it's R&D or the implementation, the commercial pilots or commercial plants, that has been increasing steadily. I think from 2016, it has increased exponentially. And this has led to, like, the investment in R&D as well as this renewed interest led to the declining of the cost of renewable technologies, as well as the rise in the efficiency of these technologies. Like the solar PV, this example started from, like, say, less than 5% efficiency, and today we have crossed 20%. At lab scale, some of the solar cells have reported even 48% efficiencies. And so with soon, I think a day will come when we would achieve such kind of efficiencies even in the commercial scale also. But that has been possible because of the increasing investment in this sector for R&D and implementation. The last point which pushes the world to go for renewable energy or supports, because the RE technologies are heavily encouraged by policy measures, banks and environmental legislations, nationally as well as globally. So at present, like when the world is concerned about the 2 degrees Celsius, like limit of climate change, crossing it, and we talk about sustainable development, the shift to renewables in this era of energy transition is no longer a choice. It's a forced or mechanical necessity for global climate stability and industrial resilience. This doesn't mean that we don't have challenges in the renewable sector. We do have a lot of challenges which need to be addressed, and we'll be talking about them when we discuss about roadmap to renewable energy scenarios. So if we look at the history of energy transition, you can see, like, the shift has, how there has been a shift towards renewable energy. So all the economic and technological advantages or the advances over the last 2 centuries, they have transformed how we produce and consume energy. If you look at this graph simply, in 1800 or before 1800, before the industrial revolution started, almost entire human race heavily relied on biomass for their supply of heat as well as food energy, and they would rely on human muscles or animals for kinetic energy, for taking things here and there, for transportation. Okay, after 1850, when the first commercial oil well was drilled, the usage of fossil fuel, mainly coal, started increasing. If you look at from 1850 to 1950, okay, before 1900 it was mainly coal, and later towards 1950 the shift towards oil started, with some emphasis being given towards gaseous fuel. But what we see in terms of renewables which came after, like say 1960s or 1970s, that segment has been increasing considerably, and this is the data for I think 2020, where you can see the share of renewables and nuclear has increased enormously compared to, like say, few decades or 1 century before. But this, at the same time, since the world population has increased exponentially, we are like 8+ billion right now, the total amount of energy consumption or the demand has increased drastically. So this global primary energy consumption has almost touched 180 terawatt hours, where the major share even today comes from coal, oil and gas. This traditional biomass is still there, but these are not accounted in the renewables. The share of biofuels coming in the renewables is different from this traditional biomass, which has been used for other purposes than electricity. So with that history of energy transition, we can see the shift towards renewables is increasing, but still we are heavily dependent on fossil fuels to satisfy our primary energy requirement. So if you look at the global investment, which I was talking previously, why it is important to study or know about renewable energy, because investment has increased in this sector a lot. So obviously the future of energy is clean and electric, and almost $2.2 trillion has been invested in clean energy in 2025 alone, where China has been the leading investor. And still with this investment, this much investment, the world's energy transition is much far from being complete. Okay, if you look at the scenario, like it shows the blue colors shows the fossil fuel. So this graph, the first bar shows the investment in fossil fuels, and second bar shows the investment in clean energy, which includes renewables, nuclear, as well as low emission fuel and energy efficiency and grids and storage part. So right from 2015 to 2025, this is the estimated figure for 2025, but if you look at 2024 also, the investment in renewable power has been increasing steadily, along with the investment in the other clean energy sources or the other initiatives aimed at providing clean and efficient energy. At the same time, the increment in the fossil fuel based investment is negligible. It has either dropped or it has either stayed constant. So it's not like new investments are not coming in the fossil fuel sector, but percentage wise or the growth wise, the investment are more in the renewable sector. And as you know, in 2016 Paris Agreement was signed, and it was that year where for the first time the annual renewable energy investment in the world surpassed or overcome the fossil energy investment. So that agreement, the Paris Agreement, which included like all the member nations of the world and all the major countries giving their nationally determined contributions, NDCs towards climate net zero, where India has given the net zero target of 2070. It confirms that the world's energy transition is ongoing, with a lot of investment being made in the renewable sector, and renewable energy is going to play a key role in this energy transition. So with that, I think we are coming towards the end of today's lecture. So to summarize, we started with the basic definitions of energy, power, work, then the type of like electrical energy, electrical power and electricity. Okay, after those basic definitions, we saw how all the energy is coming from sun directly or indirectly, and the source of that energy being nuclear fusion. Then the energy sources and their classification, primary and secondary. The other classification was renewable and non-renewable. And then we looked at the need for renewable energy or the importance of renewable energy in present world. Like it provides solutions to climate change. There has been a lot of investment, and on the basis of energy transitions history, we see that the interest in renewable energy is growing. The shift is a forced shift as well as no longer a choice now, because the fossil fuels can go down anytime. And now with recent news of like US, Israel, Iran war, you can see the impact on fossil fuels it has. So there is no stability in the fossil fuel sector. So if all the countries which have ample renewable energy resources, if they become self-sufficient and develop infrastructure based on renewable energy, in addition to having good storage capabilities, it can prepare the world better for any such unexpected conflicts also. So with that, let's stop here and thank you so much.